Okay, now it has come to my attention that I had my laptop muted manually with a button. So take 2 of part A, where we derive the equilibrium vapor composition given the liquid composition for constant relative volatility. And so we're going to start over, all over, using my phone as my second angle. Might fall over, who knows? So let's start down here. Okay, maybe it'll let me scroll down now. Okay, good. So x alpha over 1 minus x. And then we have 1 minus y is equal to y. And so what we're going to do is we're actually going to multiply this in to the parentheses, and we're going to get x alpha 1 minus x. And then you don't need that. Minus y times x alpha 1 minus x is equal to y. So then you're going to add that y to the other side once one note catches up to me. Yeah, so you have, and I'm just going to take the y out already. So y is equal to 1 plus x alpha 1 minus x, which is equal to x alpha 1 minus x. And this is going to be, once it catches up, your equilibrium vapor composition given the liquid composition for constant relative volatility, which your liquid composition is going to be your x part, right? And your vapor is your y. Oops. And your relative volatility is your alpha, which is going to be 2 later. And now we're going to derive the dynamical equations for the molar holdup and compositions for non-feed, feed trays, reboiler, and condenser. Again, didn't need to do that, but I'm gonna scroll down. Just gonna draw an example of tray, right, to go off of. You have your ZI, which is your component mole fraction. FI for your feed flow, right? And then you have your vapor coming up, your liquid coming down, and some tray holdup, right? And so then that needs to catch up. Okay, so this is going to be yi minus 1, and then for this is vapor, so it's going to be vi minus 1, and then you're going to have yi vi, right? Vapor mole fraction, vapor flow, and then you're going to have liquid mole fraction I plus 1, and then liquid Li plus 1, and then that gets stripped out. So then you're going to have X, I, and then Li, right? Then you're going to have, oops, all right, liquid holdup, or your mole holdup, Xi, your liquid dt is equal to, and so since you have your M and your X, right, you're going to be doing the positive parts first. So I like to do yi vi plus xi plus 1 li plus 1, because they're both going in. Oops. That should have been minus 1 vi minus 1. Okay, And then you're gonna subtract the stuff that's coming out, so that's gonna be your YIVI. That's coming out of the top of your tray, and then minus XILI. And we're going to add the feed, which is our ZIFI. Now we're just going to do an equation for the molar flow rates on the stage or the tray. So we're going to do dmi over dt. Okay, is equal to, and we're just going to have our VI minus 1 plus our LI plus 1, which is our vapor flow going up into the tray, our liquid flow coming down into the tray, and then minus the vapor flow coming out of the tray, minus the liquid flow coming out of the tray, plus the feed going into the tray. Yes, Luna. Is my thing dying? No. Okay, so then we're going to write this in a different form. Xi over dt is actually equal to xi dmi over dt plus, oopsie, mi over dxi over dt. That should do like multiplying, right? And then we want to get the change of the component over time by itself without the mi. So, oh boy, the cat. dmixi over dt minus xi di over dt is equal to mi dx dt. Okay, it's caught up. Now it's caught up. Okay, then we're going to divide both sides by mi, and then you're going to get a dxi over dt is equal to 1 over mi multiplied by mixi over dt minus xi over dt in parentheses. And this satisfies the other part of part A, where you derive a dynamical equation for the molar holdup in compositions for the non-feed trays, or non-feed feed trays, reboiler, and condenser trays, right? And this is because back, xi is your composition, right? M is your molar holdup, and then the dynamical part is the derivative. It changes over time. Thank you.